Research shows that over 40% of customers will abandon an application that takes over 3 seconds to load. And while it might be easy to produce a performant application for a small number of users, it quickly becomes different when we are speaking about the scale of 350 million users. Good afternoon. My name is Mike. I'm Principal Solutions Architect at AWS, and together with me is Nihan, Engineering Manager at Flo Health. And today we will speak about how Flo leverages DynamoDB to store the mission-critical data and get the predictable performance at scale. First, Nihan will start with an overview of Flo Health as a company and application so that you know it a bit better. And then she will speak about how Flo uses Amazon DynamoDB for their mission-critical data. And then I will take over for the second half to speak more about under the hood of DynamoDB. I will explain how the service is built to achieve this performance and high availability, and we'll finish with a cost optimization technique. Nihan, over to you.
Thank you. Hello, everyone. It's an honor for me to be on this stage and talk about how DynamoDB contributed to Flo's success. But first, let's talk a little bit about what is Flo, because some of you might not be familiar. Flo is a women's health app, and we are here to build a better future for women's health worldwide. We are already quite a successful app. We have more than 300 million users who have installed the app. 62 million monthly active users are using Flo on a daily basis, and 20% of women in the US are using Flo. It's a similar number in Germany and Western Europe. Flo helped 15 million users got pregnant, and I would like to deep dive a little bit more into what are the features that Flo has. We have some free features. These are part of our core offering, and users don't need to pay for these. These are things like cycle tracking, some disease detection. For example, if the users are experiencing certain symptoms like headache or cramps, they can log these in the app. We have anonymous mode because health is a very sensitive topic. The data is very sensitive. It might include information about pregnancy, about miscarriage, abortion, and even abortion is illegal in some countries. This is why Flo has introduced the anonymous mode, so there is no way to link the data back to the user in this feature. And we also have secret chats. This is where people can discuss some sensitive topics, again, such as discharge or miscarriage. This is like a forum where it's similar to Reddit or Quora. The users are completely anonymous, so they can discuss freely what they wouldn't be able to do on Facebook or Instagram. Then we have some premium features. Users need to pay to have access to these features, but it improves their lives even more, such as disease detection, polycystic ovary syndrome, or endometriosis can be detected through Flo. Improving sexual health, or if the user is already pregnant, they can monitor their pregnancy using Flo. They can improve their chances of conception, or they can improve their relationship using the partner mode. So here the key is actually that different features cater for different types of users. So Flo is highly personalized. Every user is different. Some are pregnant, some are trying to conceive, some are on contraception and trying to avoid pregnancy, some are new mom. So they all have a different goal when they are using the app. And in order to cater for this, we have developed a user profile. This is actually one of the biggest health data sets in the world. We have data about the user's age, weight, BMI, symptoms, pregnancies, some data coming from wearables such as Apple Watch or Samsung Watch. We also have some behavioral data, such as what the user searched for, or which stories they have opened, or which articles they read. So we have more than 1 trillion data points, and this is all stored in the DynamoDB. DynamoDB here is key to our success, because on an architectural level, this is how it looks. As you see, there are different data points coming from user interacting with the app manually. Some machine learning data, such as symptom predictions or ovulation predictions. Some data about LTV, like lifetime value of the user. They all get stored in this user profile data service, which is DynamoDB. And here the feature we rely on is high availability, because if the DynamoDB is down, all our app functionality is down. So let's look a little bit more into how we are using this personalization. Here we have a tool which can use certain attributes of the user to target certain traits, such as here you see the user not in a fertile window and not in ovulation. So we can use this, or marketing people can use this to show or hide certain content in the app which is relevant to that user, or they can show and hide certain features in order to personalize the experience. And we can also send push notifications based on these attributes. So how does the app look for a given user? It looks totally different, because some users are using the tracker, some are users using the insights, secret chats, some users are using the health assistant and talking to experts. Some users see the adult content, some users even see the teenager content. So let's look at how DynamoDB looks in this case. We rely on a lot of features of the DynamoDB here, such as auto-scaling. Here you see the usage is coming in waves, because we are following the sun. The user wakes up and starts interacting with the app. This is why we have an expected load in the DynamoDB. We are using the provisioned capacity for that. And we are using high availability, like I mentioned, encryption. Here, actually, the most interesting situation for us is the size of one record in the database, because we have a limit, such as 400 kilobytes. We want to store as many attributes about the user as possible, but we need to do it in a sustainable manner, because we have a size limitation, and my colleague Mike will dive deeper into that in a little bit. But it's not only about content in the app, it's also about communication timeline, because as I mentioned, we can have different personalized communication for each user, and this should also be personalized, because every user has different habits. Some wake up at 8 a.m., some wake up at 10 a.m. This is when they might be logging the symptoms. Some users have more time in the evening typically. This is why they tend to talk to the assistant later in the day or listen to podcasts in the evening. So each communication can be customized for a user, and users can also choose when they would like to receive a notification. But it turns out most users are not so different from each other. They all choose to receive it at 9 a.m. every morning. But the interesting thing is it's always 9 a.m. for us, because we have users in different countries, so it can be 9 a.m. at any time. And also the biggest stress test for us is when San Francisco wakes up and there is a spike of activity where our main users are. So let's talk about how we achieve these communications. Actually, this is very interesting, because we are using a controversial feature of the DynamoDB. It's called TTL. This TTL is made for removing a record from the database, but we are using it to send notifications. So what we do, here on top you see a statement where the users should receive a notification on their 5th day of the installation of the app. So this is when we put a record into the database with time to live 5 days from now. And when the time comes, this TTL expires, and we listen to the message from the TTL saying, oh, I'm about to remove the record from the database. And we listen to that and fire off our notifications. So here, this is how we personalize the communication timeline. Let's look on a bigger picture. On the architecture level, it looks like this. We are using many features of the DynamoDB. But the interesting thing here is that it all starts with the user coming to the app. Maybe they have just installed the app, or maybe they are here to set a goal or log a symptom. These all trigger an update on the user profile. This is why the notification scheduler constantly checks for the updates on the user profile and tries to see if there is a suitable notification now, or maybe it will be more suitable in the future. Then it puts it into this DynamoDB, which I mentioned, that uses the TTL. But we are doing this processing at a not only 60 million users a day scale, we are doing it at a 300 million users scale. Why so? Because the users don't have to come to the app and interact with the app in order to receive a push notification. So all the users who has ever installed the app is going through this processing. And this is why we are using stream processing rather than batch processing, because then we can process every user one by one. Every user needs a different frequency of notifications. Some would like to receive several notifications a day. Some users don't like notifications and they would like to receive it once a week. This is why we can personalize our notifications for each user this way. One interesting thing that happened to us, once our app has become a bit more popular and we have reached 50 million users, we realized TTL doesn't quite work for us. What has happened is that TTL doesn't have an SLA in the sense that we needed to send precise notifications, because notification might say what to expect on the first day of your period. But if you receive it the next day, it's not so relevant anymore. So in order to overcome this, we have introduced an additional service. It's called Notification Trigger. So Notification Trigger scans the database for time-sensitive notifications and tries to find what TTL hasn't sent by now, but it should have been sent, and then it tries to send it. So we are using the Notification Trigger side by side with TTL to compensate, but we haven't got rid of TTL because it comes for free, so you don't have to spend additional cost on us. But our Notification Trigger, it's a cron job which comes with a cost, so we are now using these two side by side. So let's look at how our database looks for the notifications. As I mentioned, we might have some spikes of activity. As you see in the graph as well, this is the interesting part when maybe, for example, there's a marketing communications for users in the US, or they have scheduled a notification at 9 a.m. themselves. But DynamoDB handles this really well. And here again, we rely on auto-scaling and provisioned read-write capacity, and as well as point-in-time recovery. We are storing 20 shards with 30 million items in each of them, and it takes total 3 gigabytes of space in 20 of them. And the biggest challenge here we have faced was how to work with the TTL for our use case, like I mentioned. But another very sensitive topic for us is privacy and security, because health data itself is very sensitive. But users in Flo have control of their health data. For this, we have developed the anonymous mode, like I mentioned in the very beginning. This is where the users have removed their identity and there is no way anyone can know who they are. And this feature got awarded Time Magazine's Best Inventions for 2023. And here we also are double certified with ISO for security and privacy, the highest rated certification in the world. And again, here DynamoDB have helped us. So when we are storing the personally identifiable information, we have a database called PAI, and data such as username, email, device identifier, they all get stored there. And here we again rely on features like auto-scaling, provisioned read-write capacity, but also we are using global indexes to optimize the query performance, because, for example, we need to retrieve email by user ID in order to send them some marketing campaign, and again this can cause some spikes. But the most important for us is triple encryption. Actually, when we were getting the ISO certification, we have showed this to the auditors, and they were really amazed by how secure it is, and DynamoDB have helped us achieve this certification. So Flo is already a very popular app, and as I mentioned, roughly 1 in 5 women in the US is using Flo on a daily basis. It's similar in Western Europe, but you see on the top part of the graph, it's quite dark, meaning usage is quite high. But in the southern part, the lower part of the map, it's much less. And these are also perhaps the countries that need more health literacy, countries in Africa and Southeast Asia, where people cannot afford to pay for a premium. And this is why Flo has introduced a pro-social initiative where we have launched free Flo for 66 countries in the world, including India, Indonesia, and Nigeria. This means up to 1 billion women have now access to Flo Premium. And here what's important is actually it's free for the users, but it's not free for us, right? It comes with a lot of costs. Here, actually, we have utilized how cost-effective DynamoDB is. It helps us achieve the best cost-effective usage, and this is why we can maybe afford to make it free in 66 countries rather than 65 countries. So we are very happy with DynamoDB in this sense. And now I would like to sum up our 6 years experience using the DynamoDB. Yeah, we have a quite long relationship actually. We have utilized many different features of us, such as scalability, low maintenance. Like I mentioned, the TTL, global indexes encryption has been very important for us, as well as point-in-time recovery. So we are very happy with the DynamoDB, and with that I would like to pass the microphone to Mike to dive deeper. Thank you.
Thank you, Nihan. So now I would like to speak about some of the features of DynamoDB that Nihan has mentioned, so that you can use them as well. But before I dive deep, I have just a couple of quick questions to the audience. Can you raise your hand who already uses DynamoDB in production? Wow, quite a lot of audience, so probably I'll just skip through the introduction. Cool, my second question, who is running and managing your own NoSQL database in production? Wow, that's much less. Okay, well, that makes sense, because actually running and managing your own distributed, massively scalable NoSQL database is a very challenging task. So now, as most of you are familiar with DynamoDB, I will just briefly mention some of its key features, and then we will dive deeper into the things that Nihan has discussed. So first, as you probably know, DynamoDB provides single-digit millisecond latency at scale, no matter your workload size, and it has a horizontally scalable architecture. So it means that essentially there is no limit to data or throughput that you get. And I will show just in a couple of slides how DynamoDB achieves that. It's also secure and resilient by default. So what this means is, first of all, the encryption feature that Nihan has already mentioned. So your data at rest is encrypted, but also you can enable global replication. So it's not just AZ to AZ replication, but you can replicate across regions, and that might be useful, especially for global applications like Flo. And finally, to get the access to your most critical data at any time, we provide SLA for availability of 5 nines. It's also serverless, and probably most of you know that when we say serverless, of course, we don't mean that there is magic and there are no servers. We usually mean that this is infrastructure that grows or shrinks depending on your demand. But it's not the only thing. Actually, when we just started speaking to Flo about serverless, they mentioned one very important benefit that they wanted to get. They wanted to have no maintenance or patching windows, and always be on the latest version. And that is what serverless provides as well. And finally, of course, DynamoDB integrates with the rest of AWS services. My personal favorites are, of course, the fully serverless architectures, like using DynamoDB with Lambda, with API gateway, because all of these services massively scale, and of course, they need a massively scalable database. But it's definitely not the only option. For example, Flo Health uses DynamoDB from containers inside Kubernetes, or you can use it in your virtual machines. And some recent additions after reInvent are zero ETL integrations to analytics services. So if you need to analyze data in DynamoDB, for example, you can integrate to Amazon OpenSearch service and do it there. So now with these basics covered, let's dive a bit deeper. And first, we'll start with terminology. So it all starts with a table, which can be likened to a database in relational world. Then each table contains the items, and the items can be likened to the rows. Finally, within the items, we have the attributes. And attributes are similar to columns, but not fully, because attributes don't have a strict schema. And there are only two important attributes, which are partition key, that is mandatory, and sort key, that is optional, which together make a primary key. And primary key is something that each item in your table must contain as compared to the rest of the attributes. But let's say this is a table from the first example of Nihan that contains all the user data. And in 90% of cases, we need to get a user by its ID. So what we do is we make it our partition key, A1 on this diagram, and we can retrieve the user within single-digit millisecond. But what if for the rest 10% of cases, we need to use other attributes, like for example, email address, like it is also the case in Flo? Well, we can use scan, but scan effectively reads all the items in your table and then filters only the ones needed. So it might work for small applications, but it really becomes slow when we speak about hundreds of millions of users. So another option is to use global secondary indexes, again, as Flo has done. And GSIs, global secondary indexes, are similar to materialized view. So you can define your own schema for each index. And for example, let's say if in our case email address was in the A5 attribute, we can use this second index to also retrieve users really fast. However, there are a couple important things about GSIs. First of all, each GSI under the hood is actually a DynamoDB table itself. It's only that we as AWS handle the replication for you. But it's still important because, first of all, most of the things that I will be saying about tables also apply to global secondary indexes. And second is that the data in global secondary indexes is eventually consistent. So you should note this if you have applications that need almost always up-to-date data. Except for that, there is also a limit on how many GSIs you can create. So each table can have a maximum of 20 global secondary indexes. But I would say, to be honest, if you have more than 5 or 6 in your tables, please reach out to your solutions architect at AWS, because most probably it would be possible to optimize that. And of course, it's very important when you define your global secondary index to select the partition key. The partition key in GSIs doesn't need to be unique, but we always recommend that it is a high cardinality value. And what I mean when I say high cardinality is the number of unique values compared to the number of total items in the table should be high. Like, for example, user email is a high cardinality value because most users would have different email addresses. But user status, let's say active or inactive user, is a low cardinality value because there are only 2 values for all the millions of items in the table. I will explain why it is important a bit later when we discuss how DynamoDB distributes the items. The last thing that I wanted to mention about global secondary indexes is that the capacity for each of them is controlled separately. And this is super important because, as I've mentioned, the data is replicated from the main table to global secondary indexes. So if they don't have enough capacity, your eventual consistency would become slower and slower. And this is where we come to the 2 capacity modes that DynamoDB provides: provisioned capacity and on-demand capacity. So here we will speak about 2 things. First, how DynamoDB scales tables, and of course, for that matter, global secondary indexes under the hood. And second, when should you use provisioned capacity? When should you use on-demand capacity? And the most important question is, why should you select this or that one? So let's start with the first topic, scaling. So when creating a table, you define exactly 3 parameters: the name of this table, the primary key, and the capacity mode. And with just these 3 parameters, DynamoDB knows how to distribute your items. It uses the architecture based on partitions. So here you can see the blue and pink boxes are separate partitions. So each partition contains approximately 10 gigabytes of data. And in terms of throughput, it gets 1,000 write capacity units and 3,000 read capacity units by default. So one write capacity unit can write up to 1 kilobyte of data, and one read capacity unit, or RCU, can read up to 4 kilobytes of data. And I think now it is clear why we use this architecture to achieve horizontal scalability, because each of these partitions only handles a small fraction of overall load, and that's why we can distribute it, and if we need to get more throughput, we can just split a partition into 2 separate partitions and get that throughput. So except for that, this architecture also helps us to make the data redundant, because we replicate these partitions across 3 availability zones. So essentially, to answer the first question that I've just stated, DynamoDB essentially has no limit for the data you can put into it or throughput that you can get from it. But now the question is, how DynamoDB distributes the data into partitions? Let's say we have an item. It has partition key, order ID. And then we have our DynamoDB table, which at the moment has 3 partitions, each of them with its own key space. So what we do is we have an internal hash function, and we apply it to the value of the partition key. And then we get some value inside the key space. Let's say it's 7B here. So it will go to partition B, because it is between 55 and AA. But now what happens if you also have a sort key on your item? Well, actually nothing changes. It only takes the hash function from the partition key, so it will go to the same partition. And if you have several items with the same partition key but different sort keys, let's say customer has another order, then it will go to the same partition. And within this partition, the items are ordered by the sort key in the ascending order. So what this means is that data modeling is a very important first step when you create a new application working with DynamoDB. Now, probably the second most popular and most important question that I get from my customers when discussing DynamoDB is how to choose between the capacity modes. And here, let me start with a bit of history. Initially, when we launched Amazon DynamoDB, customers had to always specify capacity for their tables. But remember what I've mentioned in the beginning. DynamoDB is a fully managed serverless database. So customers shouldn't be thinking about planning capacity. So they should have a possibility to just create their table and start working with it right away. So that's why we have introduced on-demand to provide this seamless scalability functionality. Now, how do we select between provisioned capacity and on-demand? Unfortunately, as it is most always the case in IT, the answer is it depends. And the most important factor that it depends on is the cost. But it's not just the monetary cost of operation. It is also a cost of potential throttling. Like, for example, you should ask yourself a question. Is the success of each single request paramount for my application or not? Maybe if you send the request from your user interface, it is super important, because if request fails, your user experience will deteriorate. But if it is an eventually consistent system that can repeat the requests, maybe it is less important and you can afford throttles. So now to visualize this a bit better, let's look at this diagram. Here we have time on the x-axis and partition key on the y-axis. And the diagram itself shows how application accesses the data across partitions and time. But how many of you can tell that your application really follows this evenly distributed pattern? Probably not too many. most applications would look like this. Sometimes we get bursts of traffic. Sometimes we get hot partition keys. So customers asked us to help with that, and the answer was to have auto-scaling, which, as Nihan has mentioned, Flo is using. So here you can see, well, it's not as spiky diagram as from the Flo Health, but you can still see the red line, which is the provisioned capacity, and the blue area, which is consumed capacity. So DynamoDB can increase the capacity when the demand grows and decrease it when it shrinks. It looks quite good. So why do we need on-demand after all? Well, let's look at a more extreme example. So in this case, table also has auto-scaling enabled, and initially we start with 7,500 capacity units, and the traffic is at approximately 4,000, so this is about a half of that. But then application shoots to 18,000. And in order to handle such spike, we actually also have introduced another capacity. It's called burst capacity. So burst capacity allows your table to consume more capacity units than it is configured with. But it only lasts for 5 minutes. So what happens if the spike is longer than that? Well, you see it in the bottom picture. Your request will start to get throttled. So what do we do with that? The answer is on demand. But throttling is not the only case for on demand. Actually, the first thing that customers that I work with usually use on-demand with is organic growth. Let's say you develop a new application or a new service in your application and you don't know yet what access pattern would be. You can start with on-demand. Then when we speak about small bursts, and when I say small, these are the bursts that are up to 2 times larger than your previous peaks. This is something on-demand mode handles out of the box. And finally, for large bursts that are more than 2 times of the previous peak, there may be throttling even in on-demand mode. But note the word may. DynamoDB will try to proactively split your table under the hood without, of course, any cost to you to handle larger spikes. Now, let's take a look at pretty much the same application with on-demand mode. So we are using 4,000 to 5,000 write capacity units initially, and before this diagram, the table has seen a peak of 10,000 write capacity units. So what this means is that when we hit a spike of 18,000, the table can handle it, because 18,000 is less than 2 times of the previous peak. Moreover, after our current peak, the next time the table would be able to handle up to 36,000 write capacity units. And also note the right part of this slide. If your application doesn't have a constant traffic and you don't want to pay for capacity when there is no activity, on-demand provides this to you and it can scale to complete 0. So to summarize, the answer to this question is choosing between the on-demand capacity mode and provisioned capacity mode is always a case-by-case decision. And the most important factor here is the cost of operation and cost of potential throttling. And then to choose between these 2 modes, we suggest a best practice, which by the way Flo Health has used as well, to start with on-demand capacity, assess your application access pattern, and then make a decision if switching to provisioned capacity would be more cost effective for you long term. And, and with that, we come to the last topic of our talk today, the costs. So we will speak about one technique that Flo Health has used to decrease the DynamoDB cost. So again, let's start with the basics, the same as we did in previous sections. As I've mentioned, one write capacity unit can handle up to 1 kilobyte of data. So what this means, if we write 100 bytes, it's 1 capacity unit. 1 kilobyte, still 1 capacity unit, and as soon as we cross the border of the kilobyte, we start consuming the next one. So let's return to that 400 kilobyte items that Nihan has mentioned. Of course, they are super convenient, because you just get the data from the database, and then you work with it inside your application. But let's ask a question. How many write capacity units we are using? And the answer, I think, is clear. 400 kilobytes, 400 write capacity units. And of course, this means that we will have to face some trade-offs. So first of all, DynamoDB cost is based on write capacity, read capacity, and storage. So if we consume more write capacity units, it means that we are paying more. And the same, of course, works in other direction when we read the data. Of course, more I/O cycles also mean higher latency. And basically, it's impacting your database performance. And finally, remember that I've mentioned that each partition, by default, gets 1,000 write capacity units. And if you consume 400 of them to write just one item, it means that writing 3 items per second would already lead to throttling. So now, with these basics discussed, let's take a look at how update happens in DynamoDB. So let's say we have the same partition B, there are some items there, and we need to update one of these items. So first, we look up this item from the engine. Then we update it in memory. And as the last step, we write the whole item back to the engine. So we are not writing just the update. We are always doing the update in memory and writing the whole item. So let's visualize this. Let's say we have a table like this. So here we have customer ID as our partition key and order ID as our sort key. And within the attributes, we have all the order lines. So even if this order contains several products, all of them will be stored in one item. Again, quite convenient. But what if we need to update, let's say, the quantity of oranges from 5 to 6? Maybe customer, after placing the order, but before it was shipped, changed their mind. Or maybe you have a separate field in this table, which is the status of each order line, if it was shipped or not. So what would be the size of update? Well, if it's order status, maybe it's something about 20 bytes, because it's just several characters. Looks quite reasonable. Now, let's think about how many write capacity units we will spend to update this item. So for that, we first look at the size of the item. Let's just imagine it's 20 kilobytes. Again, it's quite large. It contains all the order lines. So how much the update would cost? Well, I think you already know it would cost 20 write capacity units. Because as I've mentioned, we apply the update in memory and write the whole item. And write the whole item would consume 20 capacity units for 20 kilobytes of data. But how much should it cost in the ideal world? Well, my opinion is that it should be 1 write capacity unit, because we are only updating a small field less than 1 kilobyte. So what can you do to optimize the cost? You can break these large items into small items. And this technique is also called vertical partitioning. So this is a part of your model, of your data model design, and the part of your cost optimization exercise. But how do you actually break the items? Well, here are a couple of ideas that you can use. So first, you can use logical breaks based on your business domain, like we have just done with order lines. You can also separate your static content that doesn't change from the dynamic content that can be changed. Like, for example, let's say in your order, a shipping address can be changed by the customer after placing the order, but before it was shipped. So this would be a dynamic content then. You can also use access frequency. So how often each attribute is accessed. For example, let's say, again, shipping address. Yeah, it might be changed, but probably it doesn't happen that often. But the order status will be changed all the time, like from new to being collected, to being shipped, to being completed, and so on and so forth. And finally, you might want to think about the relationships between your data. So what data should you always receive together? For example, customer details and order details, well, they are related, but probably not directly related. In many use cases, you would retrieve them separately. So it makes sense to also store them separately. And with that, let's now again look at our example. So here we have split the order lines into 2 separate items. And we still have our customer ID as a partition key. But note that for the sort key, I'm using not just the line number, but order ID hash line number. And I will explain in just a couple of slides why it is important. But first, let's just take a look at the use case that we tried to solve. So we tried to decrease the size of updating the item. And this is what we have done here. So we just execute update item command, so for the primary key and for the sort key, and that's pretty much it. So it will update just 1 line. But remember that writing data is not our only scenario. Of course, we need to read this data as well. And reading all the lines of a single order, I would say, is quite a popular use case. So if we were using just the line ID as the sort key, we would have to execute several queries to get all the lines of our order. But using this structure, or order ID hash line number, we can use the begins with operator and get all the order lines within just one query. So what we have done with this vertical partitioning is we have improved the write performance, decreased costs, but did not compromise the read performance. That's actually not the only benefit of vertical partitioning. You can now also index on the nested data, because you cannot create global secondary indexes on lists. You can only create them on scalar data. But if you separate a list into several items, you can now do that. You can also create more fine-grained access controls using AWS IAM. And of course, with separating the items like this, you can achieve greater scalability because of the approach to partitioning that I've previously mentioned. Unfortunately, there is a trade-off still. So let's take a look at what happens when we write the item for the very first time. When it was just one item, let's say it was 50 kilobytes, we would be consuming 50 write capacity units to write it. But now, if we separated order lines into two separate items, and then the rest of the information into this 49 kilobyte item, we will be consuming 51 write capacity unit. So one extra unit to write the whole item. On the other hand, the benefit is, as I've mentioned, that you would be using just one write capacity unit for each update. So to summarize this, Flo Health uses Amazon DynamoDB to store and manage the mission-critical data. The DynamoDB tables scale horizontally because of this partition-based architecture. The data is also replicated across 3 availability zones because of this architecture. You can select between 2 capacity modes, provision capacity and on-demand capacity, and the choice depends on your use case, where the most important factor is the cost. And finally, we have reviewed vertical partitioning as a technique to optimize your data model. Of course, it's not the only technique. There are other approaches as well. And if you want to dive deeper, here are some links that you can look at. So the first 2 QR codes are YouTube videos from reInvent with advanced data modeling for DynamoDB. Actually, if you use iPhone, some iOS versions have a glitch scanning the YouTube QR codes. Just use the built-in code scanner application for that. And if you want to dive really deep to 400-level research papers, you can take a look at these 2 last QR codes that contain this deep information. Except for that, finally, you might want to use AWS Skill Builder. So this is the website that contains courses for multiple AWS services, of course, including Amazon DynamoDB. If you haven't used it, you can get 7-day free trial when you register at the URL. So skillbuilder.aws is actually the URL of the website. And that's it, what we wanted to tell you today about how Flo Health uses DynamoDB and how you can optimize your data model. Thank you. Have a great day.